So, welcome everyone to this weekly session of BioBaes community. Today, I'm going to discuss about principal component analysis, and at the end of the session, I'll demonstrate a simple coding to exemplify the coding in R for principal component analysis. So let's get started. So let's have a look about today's what is in the agenda for today. So I'll start by giving a brief introduction about me, and I'll discuss about an holistic view of machine learning and where does principal component lies in this machine learning landscape, what is it and what are the advantages of it, and what is the workflow of principal component analysis in R. And finally, I'll demonstrate some coding. So I'm a physician in Bangladesh, and I'm currently pursuing 2 masters at the same time, one in virology and another in biotechnology. And I'm also a father of 18-month young daughter. So yeah, life is pretty busy for me. And this is my kind of my situation, trying to balance my life out between all these parts. But to be honest, I enjoy this process of learning something each and every day. So yeah, I'm fortunate about that. So let's have a brief overview of machine learning. So in the AI landscape, we are trying to get a big picture. And as you can see, the artificial intelligence term is a broad term that encompasses machine learning. Intelligence refers to is any kind of intelligent machine that tries to mimic human behavior. What I mean by human behavior is that it learns on its own without being specifically programmed to do so. And machine learning algorithm is a further subset of this AI landscape, where it specifically deals with algorithms that learns iteratively and can find hidden structures in the data without being explicitly programmed to do so. And deep learning is a further subset of this machine learning landscape, which tries to reach the same solution but in a different way using artificial neural networks. So what artificial neural networks are trying to do is essentially trying to mimic the human neuronal connections in the brain. Sorry. So if we have a look at the machine learning landscape, we can see there are 3 broad categories: supervised learning, unsupervised learning, and reinforcement learning. And you may see another term such as semi-supervised learning. But these 3 are the main pillars, you can say. So in the unsupervised learning, you can see there are clustering, association analysis, and dimensionality reduction. And this principal component analysis is one of the very robust algorithms for dimensionality reduction. And it's been available for maybe for long years. It's been in the publication since 1930s or around that. So it's a very mathematically very robust, and yeah. So if we look at this picture, we can see uh, uh, the same the same classification in a different way, and with each of its uses. And if you look at the supervised learning, we can see that there is clustering and dimensionality reduction. In the dimensionality reduction, if you look closely, you'll see that 4 features of dimensional reductions are described. Feature elicitation, structured discovery, meaningful compression, and big data visualization. So these are the principal uses of principal component analysis of dimensional reduction. So what is principal component analysis? Component analysis, as I said, is an unsupervised algorithm that compresses multi-dimensional data to lesser dimensions, and it can help visualize complex data sets with minimal loss of information. And it also explains the maximum amount of variance within the data set using minimum orthogonal components. So what I mean by orthogonal components is each of these principal components are independent. So you may come across this term orthogonal. What it means is just independent components. There is no overlap between these components. That is what this is trying to basically refer to. So if we have a look at this data set and where we want to see the expression pattern of different genes in different kind of cells, such as epidermal cell, dermal cell, neuronal cell, or hepatic cell. So if we try to visualize this data for a single gene, we may be able to visualize this data using a single dimensional number line. If we incorporate one more gene, we'll probably go for a gene 1 and gene 2 on the left side of the picture, you can see. If we try to incorporate one more gene, we'll probably go for a 3-dimensional plotting. But if we try to incorporate the further genes, it gets very complex and it becomes very difficult to visualize this data. So this is where principal component analysis comes in. It will, if you have many variables or columns, it can compress it down in a 2-dimensional plot so that it is easier to visualize this data. So what are the advantages of principal component analysis? It describes more with less. Sometimes it can find hidden structure that is not apparently visible when you are trying to visualize this data using normal procedures. And since you're compressing a lot of variables into few principal components, it also reduces the computation time and it also prevents overfitting. So what I mean by overfitting is that, for example, if you try to predict something and you give a lot of independent variables to predict that output, what happens is that the model will probably be very accurate at finding the outcome from the independent variables. But if you give a lot of variables, what happens is that the model will get very attuned to the particular data set, and you probably won't get a very accurate result outside the bounds of the data set. So this is what basically overfitting means, and it is one of a very one of the main obstacles of any kind of statistical analysis. So in some cases, the principal component analysis can actually reduce in can lead to 100-fold reduction in computer processing in some cases. And as I will show you in the coding session, we'll get something similar to that in one of the data sets. So I have a GitHub repository which includes all the theoretical discussion about principal component analysis and the codes. You can get to that repository using this link. And so now let's try to figure out the principal component analysis workflow in R. So in R, if we are trying to perform principal component analysis, first we have to import some libraries and perform scaling, and then finally perform the principal component analysis. So what I mean by scaling is that, for example, in principal component analysis, higher values will have higher influence. So what I mean by that is that, for example, if you're working with variables such as height and weight, and the height is measured in meters, and the human weight is measured in kilograms, you will see that the height is probably going to fall around 1.7 or 1.6 meters, and the average weight is going to be around 70 kilograms. So as you can see from this scenario, weight, the measurement of weights are much more than the measurement of height. Multitude of magnitudes higher than the height, the weight variable. So this weight variable will influence the output of principal component analysis a lot. In order to avoid this kind of situation, we need to scale the data set so that one particular variable does not affect the principal component analysis a lot. So if you're measuring in a single unit, and all of your columns or variables are measured in a single unit, you probably don't need to worry about scaling. But if your variables are measured in different units, you probably should scale the data first and then go for principal component analysis. So when performing scaling, you may come across these two terms, centering and scaling. What centering means is that you're basically subtracting the mean from each of the individual values. And scaling means transforming the data set in a way so that the mean is 0 and the standard deviation is 1. So if you want to learn more about scaling, you can you can use this link to more about scaling, and this link describes a thorough analysis of scaling, such as normalization, standardization, centering, and scaling. You'll be able to find all of this in this link. So now let's get to some actual coding. Let me share my screen again. I think you can see my screen, right?
Yes, we can see your screen.
Okay. So first we are going to work with the iris dataset. This is a dataset R, and if we load the data first, and if we have a look at this data, what it means, you can see this set describes the sepal length and of three species flowers, specifically the Setosa virginica and can you see my screen?
Yes, we can.
Okay. So if we look at the data, you'll see that the first column describes the sepal length, the second one deals with the sepal width, the third one petal length, and the fourth one petal width. And the fifth one is a categorical variable, and principal component analysis cannot deal with categorical variables. So we have to exclude that column or variable from the actual principal component analysis part. So the way we are going to do this is, so in R, we can use PR component, that is principal component for principal component analysis. And we are going to give the iris dataset, and we are only selecting 1 to 4 columns. That means we are excluding the 5th column, and we are scaling it, and then we are centering it. Actually, the centering comes first and the scaling. So if we perform this principal component analysis, the analysis is done. And if we look at this, look at the variables or the components of PCA principal component analysis, we'll see that there are 5 names within this principal component analysis part: the standard deviation, the rotation, the center, the scaling, and the coordinate of the actual value in the principal component analysis. So if we look at the summary of this principal component analysis, we can see the first principal component describes portion of variance. That means the first principal component for 72% or 73% of the variance. And if we look at the second, it describes about 2% variance in the data set. Then together they can describe about 95% variance in this data set. So we can see that what we have done basically is that we have compressed the data from 4 components to 2 components, and yet we can still explain 95% variance within this data set. This is cumulative proportion. So this is just adds up the previous proportion of variance explained.
I think there was a slight technical issue there. So if you have any questions up to this point, you can unmute yourself, or you can post them in the chat, and then we can take them right now if there is a delay, or we can take them after the discussion is over. So, okay, there is one question. Explain the variance part. So, Sarah, can you unmute yourself and maybe elaborate your question a little bit?
Okay, thank you, Pawan. Like where I was explaining the variance, I was talking about 95%. I don't understand. Like you should just explain that columns and rows again. Thank you.
Right. Okay. So what you were seeing on the screen was that what is the proportion of each principal component. So there are 4 variables, right? So it is obvious that what we can see is that there cannot be more, the number of principal components cannot be more than the number of variables that which are there in the data set. So we had 4 variables: the sepal length, sepal width, petal length, and petal width, right? So the overall variation, that is 100%, which is the overall proportion, will be in a way divided between each principal component, right? And what he showed that the first 2 principal components covered almost 98% of the overall variation. So that is the point what Maruf was trying to make. So I think he's back now, so he can continue explanation.
So yeah, can you guys hear me?
Yeah, so there was a question from Sarah that could you please explain the proportion of variance once more?
Okay. So the proportion of variance, what it means is that how much each component is explaining in terms of variance in the actual data set. So in principle, the first principal component describes about 72% or 73% of variance within this data set. All the variances we had in this data set, it is able to, the first principal component is able to describe or explain 73% of the variance. Is it okay now?
Yes, I understand. Thank you.
Okay, thank you, great. So as I was saying, in principal component analysis plotting, you will come across these two kinds of figure. One is the script plot that you are seeing right now. So what it does is that it describes the proportion of variance explained by each of these individual principal components. As you can see, the first principal component describes the highest variance, and the second one less and less. So the another type of plot you will come across in principal component analysis is Biplot. So if we do it in base R, will be, so this is the biplot. The reason it is called biplot is because it essentially describes two things: the direction of the eigenvector and the actual scores of each of the components in the principal component analysis. So as you can see from this figure, it doesn't look very good in the base R plotting, but we can make it a little bit prettier if we wanted to, but it takes a lot of time. And there another package that does it very well called ggplot. You have to install it first. It's not available in the CRAN repository. You will have to install this package from GitHub. To do that, you need to load the DevTools library and then install the package ggbiplot from GitHub directly. As I have already have it installed, I'm not going to install it, but if you have not installed it, you can install it using these two, by uncommenting these two lines. So I'm going to load the ggbiplot library now. I have loaded it, and we can visualize this principal component analysis using Biplot, and let's have a look how this works. So as you can see, this looks pretty in ggbiplot, and it in the x-axis you can see the principal component analysis 1 explains about 73% of the variance, and the principal component 2 explains about 22.9% or 23% of variance. And these groups, the three species of the iris flowers are represented in three different colors, and we are doing this by groups, iris species. We are telling the GG biplot to color them in different color according to the species, and the ellipsoids are being drawn using this parameter, this argument of GG biplot. So this is one way to visualize in GG biplot. There is another package called Facto Extra. So if you have not already have it installed, you need to install it first, and you can just load the library. And if we try to visualize this data using Facto Extra, we can see that, so this is the script plot, and this is showing how much each individual principal component is explaining in the data set. So as you can see, we included four variables in the principal component analysis. So we have got four components. Principal component will always be equal or less than the variables you provide. So the first principal component describes about 73% of variances probably, and much prettier than the base plotting we did. And we can also visualize the biplot using this package. You can see this one.
Okay, so there was another technical issue there. So if you have any questions, I again invite you to ask at this point. If there are any questions, or do you have anything to add on to? Okay, so he's back, so you can continue.
So, yeah, sorry, I got disconnected. My internet is being very rough today. Okay, so how much were you able to see?
It
Did I
was
talk
right
about
in the library factor extra, and then you were trying to show the first scree plot, and then after that
oh,
it got disconnected.
okay, okay,
Yeah, so this particular yeah.
okay. So as you can see, we can use the factor extra package for the scree plot, and we can also use this for the biplot. So this is the biplot. Okay, so this also looks pretty good, and you can use both GG biplot and factor extra for visualizing your principal component analysis. Now we are going to do this principal component analysis using a different data set that is built into R named Volcano. So let's have a look at the dimension of the Volcano dataset. As you can see that it contains 87 rows and 61 columns. So that's a lot of columns. So if we see this data set in a more traditional way, you'll see that all of these columns and rows are numerical. So we don't need to exclude anything from the principal component analysis part. So if we perform the principal component analysis in this data set, let's do this first. And we have done it. Let's have a look at the summary of the principal component analysis for this one. As you can see, since it has a lot of uh, columns, it taking up a lot of space. But as you can see, it contains 61 principal components. And as I've already said, the amount of principal components will be equal or less than the total amount of variables you provide for the principal component. And if we go to the first two or three principal components, so the first principal component actually describes 83% of the variance in the data set, and the second one describes about 9%. So cumulatively, they totally explain 93% of this data set. So this is one extreme example of principal component analysis. As you can see, we had 61 columns, and we reduced them down to 2 or 3, and we can still explain about 97 or 93% variance in this data set using just these 2 or 3 principal components. So this is a prime example of how principal component analysis can actually help you reduce your data. So if we plot this data using the Factor Extra package, so as you can see the script plot of this data set, and you can clearly see that the first principal component is explaining a lot of variances in the data set, and the second one describes about 9%, I guess, or 10%. And we were essentially able to compress this data set from 61 variables down to just 2, and still can explain 93% or about 97% of the variance in this data set using just this 93% of this variance in this data set using just these 2 components. So this is really nice. So if we also plot the biplot using the factomine extra, and we'll probably have some idea why this principal component analysis was able to perform such a drastic compression of this data set. And as you can see, most of the variance in the data set was in the x-axis, and a few of the variance was actually in the y-axis. And that is why this principal component analysis was able to compress this data so much, and only a single principal component was able to explain 83% of the variance. So I think this goes to show how principal component analysis can really be handy in terms of in a scenario where you are bound by the limits of overfitting, and this can really come in handy, and it can significantly reduce your computation time by, and you can use this algorithm for actually significantly reduce your time in the computation processing. So this is all for today. Thank you. If you have any questions, please let me know.